All right, let's talk about the ratio test. So the statement of the ratio test is that we have a series with terms a sub k, and the ratio we're mentioning here is we want to look at the ratio of the k plus first term divided by the kth term, so the next term divided by the current term, in absolute value. And as we send k to infinity, let's call the value of that limit L. If L is strictly smaller than 1, then the series converges. If L is strictly greater than 1, the series diverges. And then if we ever have L exactly equal to 1, we just can't get any information from the ratio test. So one of the nice things about the ratio test is that there really aren't very many restrictions on when we can use it. However, there are instances where it might be more natural to try this as kind of your first test. And one of those instances is when we encounter factorials. We're going to see momentarily that there's something nice about the simplification of our ratio when a factorial is involved. I'll also note that when you have these exponential terms, such as we do here with 2 to the k, that likewise is a nice time to use the ratio test. Those exponential terms often prevent us from having this limit of L equals 1. So given that I know I want to use the ratio test here, let's think about how we would do that. First of all, I want to just refresh you on factorial. So if I have, for instance, 5 factorial, that's saying we take 5 times 4 times 3 times 1, and we stop there. So 5 factorial, we would get 2 times 3 is 6, 6 times 4 is 24, and then 5 times 24 is 120. So when you have a factorial, you take every whole number from the one that you are next to the exclamation point, multiplied by every whole number down to 1. The other thing is just we define 0 factorial to be 1. Sometimes that feels counterintuitive. And so when I'm thinking about k factorial, you just have to imagine that for whatever whole number k takes on, we're multiplying k times k minus 1 times k minus 2 all the way down to k. So in this instance, when I'm thinking about the ratio test, this is a sub k. If I need to find the a sub k plus 1, I need only then take every k that I have there and replace it with k plus 1. So I'm going to have k plus 1 factorial over 2 to the k plus 1, and then this whole thing divided by that kth term. Now, every time I use the ratio test, I know that that bottom part is going to be multiplied as a reciprocal, so you might often just jump right to this next step, that I'm really thinking of this as k plus 1 factorial divided by 2 to the k plus 1, but that's multiplied by 2 to the k over k factorial. The absolute value signs, I don't really need them here because everything is positive. However, it's a good idea to get into the habit of including them in the instances where they will matter. And the first thing I might notice here is that I can simplify this here because what I have in the bottom is the same thing as 2 to the k times 2 to the first power, and we can cancel those 2 to the k's. So this becomes now the same thing as the limit of k plus 1 factorial divided by 2 k factorial. And the question now is, how can I simplify this part? And like I said, it turns out we can do that pretty nicely. So what I'll point out here is that if you look at how I wrote 5 factorial above, within here, you'll see I have 4 factorial. So if I wanted to write 5 factorial, one way I could do that is take 4 factorial, which multiplies 4 times 3 times 2 times 1, and then just multiply that by 5. So notice that from this, in general, k factorial is always equal to k times the factorial of k minus 1. It's the same idea we can demonstrate with k equals 5 up here. So if I keep that in mind, what I can do is write this as the limit as k approaches infinity, and I'm going to rewrite the numerator as k plus 1 times k factorial. In the bottom, I have 2 times k factorial. So maybe a better way for me, just to make sure this is completely clear. So what I wrote here was true, but let's interpret it like we've written it here. So if 5 factorial is k plus 1 factorial, then 4 factorial is k factorial. And so this matches a little bit more in line with how we've written this here. So the advantage of doing it this way is now I can see that these k factorials cancel. And that was what was making our limit question so difficult. So that this now just becomes a question of what is the limit of k plus 1 over 2 as k goes to infinity. Well, that goes to infinity. And for our purposes, what I care about is that that is strictly greater than 1. So we're going to be able to say that the series now diverges. And of course, we've shown a work above, but we have to then say by what test, and the test is by the ratio test here. So this is kind of a classic example where the ratio test would be great. That factorial in there in general will make things difficult with lots of tests, but it works out nicely with the ratio test. So here's a slightly more complicated looking series. Again, notice the factorials. So that might nudge me toward using the ratio test. And so let's just jump into that and think about how we found the next term before. Again, take every k and replace it with k plus 1. So our next term should look like this. And I want to point out that we have to be very careful with replacing k with k plus 1 at the bottom. I need to distribute that 3. So kind of a warning here, a very common mistake is for somebody to write 3 times k plus just 1 and then take the factorial of that. And notice what would be missing there, because what we really have is that this is the same thing as 3k plus 3 factorial. So if somebody wrote 3k plus 1, they'd be missing 2 factors when they're multiplying out this factorial. 3k plus 3 and 3k plus 2 would be gone. And that can drastically change the result of our limit. So this is just a matter of when you replace k with k plus 1, really do think about parentheses around it to make sure that you don't forget to distribute. Now I'm going to divide by the kth term, which is the same as multiplying by its reciprocal. And we want to try to simplify. Now, what you really want to do here is try to match similar looking terms as best you can to simplify. And what I'm going to take advantage of is from the last example, I now know how to simplify k plus 1 factorial over k factorial. So right away, we can reduce this quite a bit. 3 to the k plus 1 divided by 3 to the k leaves an extra factor of 3 up top. Looking at the red terms, k plus 1 factorial divided by k factorial leaves just a factor of k plus 1 in the top, because we can express this top one as k plus 1 times k factorial. So the only thing left is we have to account for 3k factorial divided by 3k plus 3 factorial. Now we can, similar to what we did above, we can think about how to express this. So essentially when I had k plus 1 factorial, we were thinking about that as k plus 1 times k minus 1 all the way down to 1, and then observed that this was k factorial. The same thing holds true here. We just have a little bit more of a distance between these two things. So I'm going to write the top exactly as we had it. And so here, the bottom, right, that's 3k plus 3 times 3k plus 2 times 3k plus 1 times 3k times 3k minus 1. And this is going to continue down to 1. So it's just a long-winded way of writing out what that factorial looks like. But what you should observe is that what we have built in here is 3k factorial. What this really means is that I can interpret the denominator then as 3k plus 3 times 3k plus 2 times 3k plus 1 times 3k factorial. And now that means that I'm at a point where I can cancel the 3k factorial from the top and the bottom. Whoops. That leaves me with my limit of now 3 times k plus 1. And in the denominator, I have 3k plus 3 times 3k plus 2 times 3k plus 1. And I see that the degree of the denominator is larger than the degree of the numerator. So that limit is 0. 0 is strictly less than 1. So we can say then that the series now converges by the ratio test. I barely left myself enough room here, but I wanted to then also take a moment and think about the inconclusive case when L is equal to 1. So the reason it's inconclusive is that sometimes when you have L equals 1, the series actually converges, and sometimes it diverges. The easiest way to see that is think of a p-series. So if I have a p-series with terms 1 over k to the p, well, the next term would be 1 over k plus 1 to the p. And dividing by 1 over k to the p, we would get that really we want to find the limit of what we could express as this. That limit's going to be 1. So we see anytime you have a p-series, you're going to get 1 from the ratio test. But depending on that value of p, we know that the series could converge or it could diverge. So we get this whole gray area when L is equal to 1. And so keep in mind here, if ever you have a p-series, we can never use the ratio test to say anything about it. Of course, we wouldn't need to because we already have a nice result there. But this is, again, just kind of a way to think about why L equals 1 is in general problematic. But again, this is there are other series beyond p-series where you get L equals 1, and you just have to use a different test. And maybe the last thing that, as I was working through that last example, I was thinking of, maybe I'll say common mistake. So when we have 3k factorial, that is not equal to 3 times k factorial, first of all. And likewise, I can't say, another thing I might see is somebody would break it up like this. So these both are not true. I'm trying to emphasize that those are not equal. And the best way to convince yourself of that is to, pick, I don't know, k equals 4, and you can actually see that you don't get the same things there. So just be careful that 3k does need to be in parentheses, and the factorial really just applied to the whole product there.